Hello friends and welcome to YouTube channel on Engineering Mathematics by Dr. Navneet. So today we are going to start with new chapter. So name of chapter is Higher Order Linear Differential Equations with Constant Coefficient. So in this video lecture we are discussing about the definition of linear differential equation with constant coefficient, then the operator D, then complete solution of linear differential equation with constant coefficient, which is the sum of complementary function and particular integral, and our main focus is on finding the value of complementary function. So let's start with the definition of linear differential equation with constant coefficient. The general form of linear differential equation with constant coefficient is of the form a naught nth derivative of y with respect to x plus a1 n minus 1th derivative of y with respect to x plus a2 n minus 2 derivative of y with respect to x plus and so on plus a n minus 1 dy by dx plus a n y is equal to capital X. So in this general form of linear differential equation with constant coefficient, the term a naught, a1, a2 and so on up to an, these terms are constant, which may be positive or which may be negative, and capital X is a function of x only, or this may be constant. So such type of equation is called as linear differential equation with constant coefficient, and in short we are abbreviating this equation by LDE. So LDE stand for linear differential equation. So now some examples are given. So here we mention the examples which is related to second order, third order and fourth order, and in this example, so coefficient a naught, a1 and so on, so this coefficient may be positive, may be negative, whereas the right hand side of this equation capital X is either exponential function, so this may be constant, may be 0, or maybe sine x cos x, or sine of 4x cos of x sine of 2x and so on, or it may possible that this right hand side is the product or sum of algebraic, linear and trigonometric equation. So this is the definition of linear differential equation with constant coefficient, and examples are also mentioned. Now let's define the operator D. So D be the symbol which denotes the derivative with respect to x. So that means D stand for D is equal to d by dx, that means derivative with respect to x. Therefore dy indicates derivative of y with respect to x. Again d into dy, which means d square y, which indicate the second order derivative of y with respect to x. So in this way we can generalize this term as d raised to ny indicate, or d raised to ny denotes the nth order derivative of y with respect to x. If we put all the value of operator D in the definition of linear differential equation with constant coefficient, then we can write definition of linear differential equation with constant coefficient as a naught nth derivative of y with respect to x means d raised to ny plus a1 n minus 1th derivative of y with respect to x means d raised to n minus 1y plus a2 n minus 2 derivative of y with respect to x is denoted by d raised to n minus 2y plus and so on a n minus 1 into derivative of y with respect to x is denoted by dy plus a n y equal to capital X. So if we observe this equation, then in this equation on the left hand side y term is common. So if we take the term y common from left hand side, then we get equation as a naught d raised to n plus a1 d raised to n minus 1 plus a2 d raised to n minus 2 and so on, plus a n minus 1 d plus a n y equal to capital X. So in brief, we can represent linear differential equation with constant coefficient as f of d time y is equal to capital X. So this is the brief representation of linear differential equation with constant coefficient, where in this equation the term f of d is a polynomial in terms of d with degree n. So this is the conversion of linear equation in terms of operator d. So if we write the term f of d time y is equal to 0, that means if we take the right hand side value of linear equation as 0, then such type of equation is called as associated equation. And if we only take the value of f of d is equal to 0, f of d is equal to 0 means polynomial in terms of d is equal to 0, then this equation is called as auxiliary equation, and we are abbreviating this auxiliary equation as AE, where AE stand for auxiliary equation, and this auxiliary equation plays very important role for finding the value of complementary function. Now without going into the theoretical discussion, for solving the general linear differential equation with constant coefficient of the form f of d time y is equal to capital X, the solution of this equation involves two parts. So first part is called as complementary function, its abbreviation is CF, and second solution part is called as particular integral, again its abbreviation is PI. Hence the complete solution of linear differential equation with constant coefficient is the sum of complementary function and particular integral. Again, in short, we are abbreviating this as CS is equal to CF plus PI, or in terms of notation we call this as Y is equal to YC plus YP, where YC stand for complementary function and YP stand for particular integral. So some people may call complete solution as general solution. That means complete solution is also called as general solution. So in short, we may abbreviate this as GS. So once again, revision. So the complete solution of linear differential equation has two parts. One is called as complementary function and second is called as particular integral. Now question is that how to find the value of complementary function. So now complementary function is obtained by solving auxiliary equation. That means for getting the complementary function of any linear differential equation with constant coefficient, first solve the auxiliary equation. Auxiliary equation means the equation which is represent in terms of d, that means polynomial in terms of d with right hand side as 0, which is called as auxiliary equation. So depending upon nature of roots of auxiliary equation, there are three cases. So that means indirectly complementary functions are of three types. So let's assume that f of d time y is equal to capital X be a linear differential equation. In briefly, we are representing a linear differential equation by this notation. And after solving this linear equation, after solving the auxiliary equation, let's assume that m1, m2, m3 and so on up to mn are the root of the auxiliary equation. So auxiliary equation is of order n, that's why we get n root according to the fundamental theorem of algebra. Now let's discuss the first case. So first case is that auxiliary equation with real and distinct, that means non-repeated root. In this case, the value of complementary function is equal to yc which is equal to C1 e raised to m1x plus C2 e raised to m2x plus C3 e raised to m3x plus and so on plus Cn e raised to mnx. So this is the first formula for obtaining the value of complementary function. Only put the value of m1, m2, m3 and so on up to mn, we get the value of complementary function. Now to understand this first formula for obtaining the value of complementary function, so let's take the example. So example is, evaluate the complementary function of the equation second order derivative of y with respect to x minus 5 times second order derivative of y with respect to x plus 6y is equal to 0. So in this equation, if we try to find the value of complementary function, then first convert this equation in terms of operator d. So if we write d is equal to derivative with respect to x, then d square stand for second order derivative with respect to x and so on. If we put operator d in the given equation, then given equation becomes d square y minus 5 dy plus 6y is equal to 0. So y is common from the left hand side. If we take the term y common, then we get equation as d square minus 5d plus 6y equal to 0. So our aim is to find out the value of complementary function, and we know that complementary function is obtained by solving the auxiliary equation. So in this equation, auxiliary equation is d square minus 5d plus 6 is equal to 0. So now try to solve this equation with the help of quadratic form, or we may apply the concept that find a number whose product is 6 and whose addition is minus 5. If we try for the number minus 2 and minus 3, their product is 6 and the addition of minus 2 and minus 3 is minus 5. That's why, so this may be the root of the given equation, or you may directly apply the quadratic equation formula for obtaining the root. Once again, if we write the given equation, that means if we split the middle term minus 5d in terms of minus 2d and minus 3d form, then we get the equation as d square minus 2d minus 3d plus 6 is equal to 0. So from the first two term, take d common, then we get d minus 2. Again, from next two term, take the term minus 3 common. So after taking minus 3 common, we get second bracket as d minus 2. So if we take the term d minus 2 common, then we get next step as d minus 2 and d minus 3, which is equal to 0. As the product of two number is 0, then either one of them must be 0. According to this rule, d minus 2 is equal to 0 and d minus 3 is equal to 0. If we simplify this equation, then we get the root of given linear equation as d is equal to 2 and 3. So if we observe this root carefully, then these roots are real and non-repeated. So then according to the complementary function formula for writing the roots for real and non-repeated value, complementary function is equal to yc is equal to c1 e raised to 2x plus c2 e raised to 3x, because the value of first root m1 is 2 and the value of second root m2 is 3. That's why we can easily write the value of complementary function with the help of standard formula. So now this is the example which is related to the auxiliary equation with real and non-repeated root. So now let's discuss the second case, auxiliary equation with real and repeated root. That means when we solve the auxiliary equation and after getting the roots of auxiliary equation, it may possible that some root may get repeat. So whenever root get repeat, then how to write the value of complementary function? Suppose assume that two roots are repeated. Assume that first root m1 is equal to m2. That means m1 is repeated twice. Then complementary function is equal to yc, which is equal to c1 plus c2x e raised to m1x plus c3 e raised to m3x plus and so on. So in this way we can easily write the value of remaining root. So this is the formula when two roots are repeated. Similarly, it may possible that three roots may get repeat. Suppose first root m1 is equal to m2 is equal to m3. That means first root m1 is repeated thrice. So in this case, the value of complementary function is c1 plus c2x plus c3 x square after bracket e raised to m1x plus c4 e raised to m4x and so on for the remaining roots. So this formula is applicable for finding the value of complementary function when three roots are repeated. So we can easily generalize this formula so with the help of previous two steps. So this is the case number 2 for obtaining the value of complementary function when roots are real and repeated for the auxiliary equation. Now to understand this complementary function case number 2, let's take the example. So now here example is evaluate the value of complementary function for the linear equation d square plus 4d plus 4 into y is equal to 0. So if we try to find the value of complementary function, then we know that complementary function is obtained by solving the auxiliary equation. So in this equation, auxiliary equation is d square plus 4d plus 4 is equal to 0. So we may directly solve this equation with the help of quadratic equation, or we may apply the concept that find a number whose product is 4 and addition is also 4. So last term is 4 and middle term is also 4. That's why product 4 as well as addition is also 4. So 2 into 2 is 4, again 2 plus 2 is 4. So if we split the middle term 4d as 2d into 2d, then we get equation as d square plus 2d plus 2d plus 4 is equal to 0. From the first two term take d common, again from the second two term take 2 common, then we get the factor of this equation as d plus 2 and d plus 2 is equal to 0. That means product of two number is 0, either one of them must be 0. So then d plus 2 is equal to 0 or d plus 2 is equal to 0. So then if we simplify this equation, then we get the value of root of the given equation, which is d is equal to 2 and 2. So if we observe this root, then these roots are real and 2 is repeated twice. That's why roots are real and repeated. So according to the complementary function formula for real and repeated, so we can write the value of complementary function as yc is equal to c1 plus c2x e raised to 2x. Now this is the example where two roots are repeated. Now let's take the next example where three roots are repeated. So formula for three roots are repeated formula is given. Then for the evaluation of complementary function, linear equation is given as d cube minus 3d square plus 3d minus 1 into y is equal to 0. So for obtaining the value of complementary function, auxiliary equation of the given linear equation is d cube minus 3d square plus 3d minus 1 equal to 0. So now observe that this equation is the perfect cube of d minus 1. That means d minus 1 its cube is equal to 0. So if we try to solve this equation, then we get the value of root of this linear equation as d is equal to 1, 1 and 1. That means 1 is repeated thrice. That means root is repeated 3 times. Then according to the formula for obtaining the complementary function, when roots are real and repeated, so we get the value of complementary function as yc is equal to c1 plus c2x plus c3 x square e raised to x. So in this way we can easily find the value of complementary function of a linear differential equation with constant coefficient. Now let's discuss the case number 3. So methods of finding the complementary function, case number 3. So auxiliary equation with complex root, or some people may call this as imaginary root. So auxiliary equation with complex or imaginary root. So let's assume that alpha plus beta I is one of the root of auxiliary equation. Then according to the complex number property, alpha minus beta I will be the another root of the auxiliary equation. Then when the roots are complex, then complementary function is equal to e raised to alpha x in bracket c1 cos of beta x plus c2 sine of beta x. So this is the formula for finding the value of complementary function when roots are complex. Again, it may possible that in complex roots, root may get repeated. That means if the roots are complex repeated, that is alpha plus minus I beta and alpha plus minus I beta are repeated, then in this case complementary function is equal to e raised to alpha x, then in bracket c1 plus c2x into cos beta x plus c3 plus c4x into sine of beta x. So this is the formula for obtaining the value of complementary function when roots are complex. Now to understand this concept, take the example. So for example, evaluate the complementary function of the linear equation d cube minus 3d square plus 9d minus 27 into y equal to 0. So this is linear differential equation with constant coefficient. Our aim is to obtain the value of complementary function. To obtain the value of complementary function means solve the auxiliary equation. So here the value of auxiliary equation is d cube minus 3d square plus 9d minus 27 equal to 0. So observe that this is cubic equation. Then for solving such type of cubic equation, synthetic division method is applicable. So according to the synthetic division method, so write down the given equation in terms of decreasing power of d. So in this equation already equation is in decreasing power of d. So now write down the coefficient of this equation. So coefficient of these equations are 1, minus 3, 9, minus 27. Then so according to the rules for finding the factor of this cubic equation, so minus 1 is the root of given equation if the sum of alternative coefficient is 0. So here sum of alternative coefficient is not 0. So d is equal to plus 1 is the factor if the sum of all coefficient is 0, but here sum of all coefficient is also not 0. Then find the divisor of last term. So here last term is 27. So divisor of 27 is 3. So last term is divisible by 3. That's why we take the term 3 as the factor of this equation. So now keep 1 as it is. So 1 into 3 is 3. So plus minus 3 plus 3 is 0. Again 0 into 3 is 0. 9 plus 0 is 9. Again 9 into 3 we get this as plus 27. So minus 27 plus 27 equal to 0. So we get remainder as 0. That means 3 is the factor of given linear equation or given auxiliary equation. So now so we get factor of this equation as d minus 3. So write down the opposite sign because 3 is the root of equation. So to get the root of equation, so we write this equation as d minus 3. Then d square plus 9 equal to 0. If we solve the first bracket d minus 3 equal to 0, we get the value of d is equal to 3. And if we solve the term d square plus 9 equal to 0, we get the root as plus 3i and minus 3i. So because of the imaginary term I, so these roots are complex. So as the roots are complex, then according to the complex root formula, complementary function, so here complementary function is obtained by complex root, so where alpha is equal to 0 and that of value of beta is 3. So irrespective of the sign, either plus or minus, so value of beta is 3 and value of alpha is 0. So for the first root d is equal to 3, we can write this as c1 e raised to 3x plus next two roots are complex, so e raised to alpha x, value of alpha is 0, so e raised to 0x. In bracket already we write the constant c1. Now next constant is c2 into cos of beta, value of beta is 3, so cos of 3x plus c3 sine of beta, that means 3x. So in this way we get the value of complementary function of the equation when roots are complex. So let's summarize this lecture. So if any linear differential equation with constant coefficient term is there, then this equation has two type of solution, which is the sum of complementary function and particular integral. Then for finding the value of complementary function, so complementary function is obtained by solving the auxiliary equation, and auxiliary equation, depending upon the nature of roots of auxiliary equation, there are three cases. So first case is that auxiliary equation with real and non-repeated root. Second case is auxiliary equation with real and repeated root, and third case is auxiliary equation with complex root. That means there are three different cases for obtaining the value of complementary function. Friends, I hope you like this lecture. So thanks one and all.